Hi everyone, I'm Tim Wolf from the Wolf Circle. In this video I will discuss three fundamental kinematic equations, including displacement, velocity, and acceleration. Starting with displacement. So displacement equals the final position minus the initial position. Let's do a quick example to illustrate this. So an athlete hits a tennis ball from the service line, which is 10 meters from the back of the court, to the net, which is 20 meters from the back of the court. This is where we use the displacement equation because we're given two different non-zero position values. Assuming that the tennis ball barely doesn't make it over the net, it ends up right on the position of the net. Then substituting the values into the equation for final and initial position will give us 20 meters minus 10 meters. Thus, the displacement value will equal 10 meters. It is worthy to note that the final minus initial equation can be used for any change in variable, not just displacement. So, for example, using change in velocity, which you'll actually see later in this video, then like displacement, change in velocity equals final velocity minus the initial velocity. Now let's define velocity. So velocity equals displacement over change in time. Thus, velocity is a measure of the rate of change in position. Note that any variable divided by change in time is a measure of the rate of change in that variable. Here's an example using the tennis ball from the earlier slide. Say it traveled those 10 meters in only 2 seconds. So substituting the values into this equation will give us 10 divided by 2, which equals 5 meters per second. That is a very slow tennis ball. But velocity is a vector quantity, meaning that it has direction. So if I draw a very squiggly line beside this one, then these two lines still represent the same velocity, even though the blue line covers a greater distance. Speed equals distance over time, while velocity equals displacement over time. And displacement is only dependent on the object's initial position and final position, and not the path. Velocity is used much more heavily in most physics classes. Finally, let's define acceleration. So acceleration is the change in velocity over change in time. Thus, acceleration defines the rate at which velocity increases or decreases. Let's try a different example, where a car at constant acceleration accelerates from rest to a velocity of 20 meters per second in only 10 seconds. So substituting these values in to the equation, then we get 20 meters per second over 10 seconds, giving us an acceleration of 2 meters per second squared. You may have noticed that all of the variables that we used today have a different unit. Displacement has meters, velocity has meters per second, and acceleration has meters per second squared. That is because when converting units, you apply the same factors as you do the values in an equation. So for this example, using the velocity equation, since you're dividing displacement, which is the unit of meters, by time, which is the unit of seconds, then you also divide the units, meters, divided by seconds. So you're given the unit of velocity, which is meters per second. That's all for today. Thank you so much for watching, and I'll see you all next time.